Hello and welcome to another chemistry topic together. If you are taking these or watching this video on the first day it was assigned, you can fill in the date as shown. If you're watching this video at any other time for any other reason, I welcome you and I'm excited to talk some chemistry with you. The topic for today that we'll be covering is electronegativity values and Lewis dot diagrams. Go ahead and set up your focus notes with your topic and your date, and then the essential questions we will be answering in this lecture. There's two of them. One, how do I use electronegativity values to determine what type of bond will form between two elements? And how do I use Lewis dot diagrams to represent elements and ions? So kind of an introduction to some more details about bonding. That's the focus of this lecture. All right, pause the video if you need to finish setting up your notes. Otherwise, let's get into it. So the first thing we want to talk about is just this idea of becoming a bond. So you're not an element, you're not an ion, but turning into bonds, what does that even mean? So why do atoms connect with other atoms? Why don't they just stay all separate? Well, the big reason is that they're trying to be stable. That's true of really everything in the natural world, trying to be stable. And in chemistry, that means that the S and the P sublevels in the electron cloud are filled. So how does that happen? It's about electronegativity. So remember, the definition of electronegativity is how good is an element at attracting another electron from a different atom, right? So if I'm an element, how good am I at attracting other elements' electrons into my electron cloud? So a visual here. So you've got, this is your positive nucleus. It's attracting its own electrons. But then if you have a very effective nucleus, not a lot of shielding, a pretty small atom, it can attract electrons to its from a different place to its own electron cloud. So that's kind of what this animation. So like this is kind of a fight between, so is it this nucleus that's going to win and take this electron into this electron cloud, or will this nucleus win and take this electron into its own electron cloud? And the way it will work is it depends on electronegativity. If one electronegativity value, or if one electronegativity sense or ability is much stronger, it can actually pull the electron over. If it's they're kind of evenly matched, they might kind of tug back and forth, and that determines what type of bond will be present. So the nucleus is pulling on electrons. That causes the connection. There's two types. Either one of the nucleus is so much stronger, it can actually pull the electron from the other electron cloud into its own electron cloud. That creates ions, and then the connection is an ionic bond. Or both nuclei are pulling on their own electrons and the electrons of the other atom, but not really strong enough to actually take the electron. And then you create that sharing of electrons called a covalent bond. All right. So like we just said, an ionic bond occurs when between two elements, when an electron has been gained by one atom and lost by another atom, and then you create that thing called a formula unit. So here's a visual. So we've got one atom here, another atom here. This nucleus must have been so strong that it actually attracts this negative electron to this electron cloud, meaning now I transferred an electron. This is a negative ion. This is a positive ion. Well, in the science world, the natural world, positive and negative charges attract. So the connection between them, they are now stuck together based on that attraction, and that is called an ionic bond. And this whole thing would be called a formula unit. So for covalent bond, this is when elements are sharing. So this is the idea of, okay, so here's a nucleus attracting these negative electrons. This nucleus is attracting these electrons. So both nuclei are attracting these shared electrons. That creates a molecule because the two elements are now connected by that shared pair of electrons, and that creates a molecule. So the connection is called a covalent bond. The whole result is referred to as a molecule. So just reviewing a bunch of different little kinds of vocab terms. All right. Now it turns out that there's two ways you can share. So you can do a sharing where one atom has a noticeably stronger nucleus. It's not strong enough to create an ionic bond. It doesn't actually take the electrons, but it's really pulling the electrons closer to itself. Think tug of war. Two teams are holding the same rope. One team is a lot stronger, so it pulls the rope, and the other team is losing, but doesn't completely lose, right? So it doesn't lose the game, it's just getting pulled towards the other side. That creates what we call partial charges, and they're used by these Greek letters, delta, lowercase delta, delta positive, and delta negative. We don't put full positives and full negatives because those are for ions. So this is how we tell the difference between an ion versus a polar covalent bond, these partial charges. Here's a visual. This is hydrogen's electronegativity value. This is chlorine's electronegativity value. The difference between them we can see is 0.9. So it turns out that difference is not so strong that chlorine can actually pull an electron from hydrogen, but it tugs it towards itself. Well, because it's tugging the electrons closer to itself, it's partially negative because electrons are negative, leaving hydrogen partially positive, and that result is referred to as a polar bond. Think of kind of how there's like north and south poles on a magnet. That's kind of what this is. So there's a place that's kind of positive and kind of negative, just not as obvious as an ionic bond. The other option for sharing is nonpolar. The two nuclei in the molecule are both relatively similar in strength. It doesn't mean they're both weak. They could both be really strong, but they're the same kinds of strong. So then they share electrons equally. So for example, if we had two chlorine atoms, well, up here, chlorine was stronger than hydrogen and created that partial negative area, right? Well, here the chlorine is sharing with another chlorine. So even though they're both strong, they're equally strong. So there's no place on the molecule that is more positive or more negative than the other, and that's called nonpolar because there's no poles in that bond. Okay, so again, both of these are examples of sharing electrons, but there's a nonpolar way to share and a polar way to share. And again, it has to do with the nucleus strength. Okay, so then how do we determine that bond? How do we decide if is it polar, is it nonpolar, is it ionic? Well, it's again based on electronegativity values. So when you look up the values between two atoms that are bonding, the difference between them will decide, is the electron actually lost? Is there something being gained, or is it being shared? A small difference between the two values means it's more likely to share, and a larger difference means it's more likely that one atom can actually take away an electron, meaning one loses and one gains. And that's what we're going to focus on next. So I've got a nonpolar. Is it nonpolar, or is it polar covalent, or is it an ionic bond? So you look at electronegativity values between the elements and figure out what they start at. If the atom has a much higher electronegativity value, it will pull on the electrons more. And if it's actually strong enough, it will actually take the electrons. You have on Schoology, or I've given it to you in person, that fancy periodic table. On the back of it are electronegativity values. And the differences between the electronegativity values is shown on the top of the back of the fancy periodic table in black writing. And then the percent ionic character is in red writing. And so basically we're saying, well, if it's a high percent ionic character, it's more likely to be an ionic bond. If it's a low percent ionic character, it's more likely to be a nonpolar bond. That's kind of the idea. And here's the general percent values that we use in chemistry, but there's a little bit of overlap. But if it's a low percent ionic character, that means it's not really an ionic at all. It's nonpolar. If it's kind of in the middle, you can have a weak polar or a strong polar, meaning, yeah, there's a difference between the two nuclei, but it's not super obvious. So you get those polar bonds. And then if the percent ionic character is higher than 50, then we say, okay, one of those atoms is strong enough, the nucleus actually pulls the electron away, and then you create those ions in an ionic bond. Okay, so how do we do this? So find the periodic table that looks like this. Either I gave you one in person or there's one posted on Schoology, and look on the back side. Or you can find any periodic table that shows electronegativity values. On the top of the backside, there's this chart. So it's the percent ionic character. And look, difference between the electronegativity values corresponds to the percent ionic character. And then the electronegativity values in the periodic squares are the upper right black number, right? So hydrogen is 2.20, beryllium is 1.57, fluorine's 3.98. And so that is the number we're looking for electronegativity value. we'll subtract two values to get the difference, and then that will correspond to the percent ionic character. So what type of bond? So remember, these are our guides. Nonpolar is a low percent difference, ionic high percent difference, and then in the middle is your polar covalent. How about this one? Nitrogen dioxide. So we might use the estimate that says, oh, these are both nonmetals, so I bet it's covalent. But that's really just a shortcut. As chemists, we need to know the details. Well, why is it covalent, and what kind of covalent is it? So I look up the values on the back of that periodic table or anywhere that you can find electronegativity values. Nitrogen is 3.04 and oxygen is 3.44. Now, it doesn't matter that there's two oxygens because the bond only happens between one N and one O at a time, and then there'd be another bond between N and the other O, but it's the same kind of bond. So don't let those subscripts fool you in the formulas. They don't change the work that we're doing here. So these are the two values. We find the difference between them. So that just means subtract them. Doesn't matter which one is first, but you need to have a positive value. So subtract the smaller from the bigger. 0.40 is the difference in electronegativity. So that was this. The difference in electronegativity was 0.4. So I look here. That corresponds to the percent ionic character, which is 4. And then we look up here and say, oh, a 4% difference is a nonpolar bond. So the bond between nitrogen and oxygen would be nonpolar, meaning these two nuclei are pretty similar. And if you look at where they are on the periodic table, they're right next to each other. So there's not a huge difference between their two nuclei. And so when they go next to each other to make a connection and help each other be stable, neither one really pulls the electrons more than the other, but this oxygen is attracting these outer electrons, this nitrogen is attracting these outer electrons. That creates the connection, and it's a non-polar bond. All right, let's try one more. So still the same things. Let's now do boron trichloride. So again, this 3 just means that overall you have one chlorine bonded to the boron, like in this direction, another in this direction, another in this direction, or three-dimensional direction, that kind of thing. But it doesn't change the math or the chemistry we're going to do. So boron's electronegativity value is 2.04. Again, you can look that up on the periodic table or anywhere where you can find electronegativity values. And chlorine is 3.16. Okay, I need to know the difference between them to see how much difference is there between the two nuclei. So I subtract them, I get 1.12. I look on that list. So 1.12, well, it's somewhere between here, right? So somewhere around here. So percent ionic character, somewhere around 27. All right. A 27% difference falls in this range, meaning that's a strong polar bond. So the bond between boron and chlorine tells us that this chlorine is pretty strong, and it's almost strong enough to take an electron from boron, but not quite. So instead, they're sharing electrons, but chlorine is kind of a bully and is pulling this pair of electrons between boron and chlorine a little bit closer. So remember that delta symbol? So like this would be delta negative, partial negative charge on chlorine because it has the higher value. It's pulling the electrons a little closer, and electrons are negative, leaving boron partially positive. So having those partial positive and partial negatives is important for why some things mix with water and other things don't mix with water, and lots of other things. It could be about boiling point and melting point. All of those things kind of matter, and that's kind of where we're going with this unit. All right, go ahead and take a pause right now. That was a lot of information. I realize that. So you can either just pause right now, do your level 1 question, something right from the notes, or you can actually pause and take a big break and finish these notes later because the rest of our notes are about the same amount of notes that we've already had. So it just depends on how much time you have right now. But for sure, pause, do your level 1 question, kind of stretch a little bit, rest your eyes if you need to, time to take a break, and come back. We've got about half our notes left. So even though it's only level 1, this is just kind of a nice break for level 1, and then we're going to add on a little bit more. All right, here we go. So if you're continuing on, welcome back. Let's talk next about atoms being stable, because remember, that's one of the whole reasons that bonds form, and that was the first part of our notes, was thinking about what types of bonds are there. Is it ionic? Is it polar covalent? That kind of thing. Well, next we want to talk about, well, why is making ions more stable? Because you become an ion to try to make an ionic bond. So let's focus on that. Well, the first thing we need to review when we're talking about stability is we need to review a valence electrons. Remember, those are the electrons in the outermost energy level, not sublevel, not orbital, energy level. So really you're looking at the electrons that are in the highest S and P sublevels. Like, is it a 4s and a 4p? Is it a 5s and a 5p? That kind of thing. So like, for example, if you had a 5s and a 5p, you would also have a 4d. That is not the outermost energy level, because a 4d is a lower level than a 5s and a 5p. It's that number, the big number, the principal quantum number. So for example, strontium, if you look on your periodic table and you look at how many electrons it has, this is the electron configuration. So you would start with the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. So I've got 10, 18, 19, 20, 36, 38 electrons. That's strontium. But the valence electrons are the ones in the highest S and P. So the highest S and P, so there's a 5S, there isn't a 5P, there's a 4P, but this is a higher level. So this is your highest energy level. There are 2 valence electrons in there. All of these would be lower electrons. These are your valence electrons, all right? Germanium, so starts the same way, 1s2, 2s2. You're looking at your periodic table, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. And then there's also, I went too far. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. So it's element number 8, 9, 10, 18, no, wait, did I count that right? So 10, 11, 12, 18, 19, 20, 32. Element number 32. So again, if we want to figure out the valence electrons, we look for the electrons in the highest S and P. So there's a 4p. Well, if there was a 4, if I made it to 4p, there had to have been a 4s. Oh, yep, here it is. So you count together the 4s2 and the 4p2. Those are your valence electrons. So the highest occupied S and P sublevels in that order. So if there's an S, you count that. If there's an S and a P, you count them together, but you would never count just a P. Because again, if you made it to a P high level, there's also an S high level. So S and P go together. All right, how about sulfur? 1s2, 2s2, 2p6, 3s2, 3p4. Electrons in the highest S and P. There's a 3p4 and a 3s2. They're both level 3. So the highest level is both of those, 6 valence electrons. Okay, so visual. So here's our periodic table. So again, what we're looking for is the highest S and P sublevels. So if I'm looking at here like antimony, I can just, without even writing out the full electron configuration, I can just say, well, antimony is in the P block, so it has 1, 2, 3 in the P block, and then it would have also had S1 and 2. So 1, 2, 3, 4, 5 for antimony, 5 valence electrons. Because again, the D block and the F block won't ever be your highest energy level. Those are just high sublevels. So for example, acetine is right here. So 1, 2, 3, 4, 5 in the P block, 1, 2 in the S block of that same row. So S2 and P5, there's 7 electrons in astatine. And then, like, for example, radium would just have 1, 2, because it only has an S. It doesn't have a high level P because it's right here. It stops in the S block. So you're just counting no matter what element it is, you're just counting the S and the P. So for example, molybdenum, well, molybdenum is in the D block. Its highest energy level would have been the 5s2. So 1, 2 for molybdenum. Tungsten also 1, 2 valence electrons. Silver would be 1, 2 valence electrons. So because the D block is a lower energy level, even though it's a higher sublevel, you only count the highest energy level. So in this case, like all the elements in the D block, they would all have 2 valence electrons because of the S2 block being filled. Okay, so that's a review. So that's one of the things. So remember that filling the S and the P is every element's goal. So then that brings us back to why the noble gases have 8 valence electrons. Why 8 is the magic number? Because 1, 2 from the S and 1, 2, 3, 4, 5, 6 in the P. 2 and 6 is 8. So all of these noble gases have 8 valence electrons. But helium only has 2 because it doesn't have a P block. It's just the S block filling. Okay, so let's show how to represent this. It turns out that a while ago, over 100 years ago, there's this guy named Gilbert Lewis who was like, I want to have a way to represent how stable an element is. Just a quick little diagram. So what it does is you write the element symbol and you put the valence electrons as dots. That's why they're called Lewis dot diagrams, to show how close is that atom or that ion to being stable. Let's do a couple examples of that. All right, first one. Sodium atom. So you would look at where sodium is. It's in the S block, and there's only one electron in that first S column because this is the electron configuration. 1s2, 2s2, 2p6, 3s1. Or again, just look at where it is on the periodic table. It's in the first column of the S block. So 1 is the highest energy level, 1 electron in the highest energy level, 1 valence electrons. So sodium, put the symbol Na and 1 dot. This shows me that sodium is not very stable, right? If it got rid of this electron, look, if it got rid of it, it would have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, because then the highest level would be 2s and 2p. So that gives us a hint about what's going on. In fact, let's draw that. What about the sodium ion? Well, we know from before that the oxidation number for sodium is a positive 1. It wants to lose an electron to be stable. But now we can talk about why. Because again, if it loses this outer electron, the highest energy level is a 2. And there's a 2s2 and a 2p6. There's 8 valence electrons. So we start with the symbol, and then we give it its 8 dots. But remember, these can't both be right. Wait, does it have 1 dot or 8 dots? Well, so the other piece, if you have an ion, you need to represent that with brackets and the charge. What did it do to get 8 valence electrons? So sodium has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons from the 2s2 and the 2p6. The brackets and the +1 charge tell you it only looks like this, the 8 dots, because it lost 1 electron. Let's try another one, see if this makes sense. Fluorine atom. If you look at the electron configuration for fluorine, so it's 1s2, 2s2, 2p5, because it's 9 electrons. But then you also could look, fluorine is in that 5th column of the P block. So you count the P and the S, 1, 2, 3, 4, 5, 6, 7 valence electrons. So for the fluorine atom, the Lewis dot diagram is a capital F for the symbol for fluorine, and then 1, 2, 3, 4, 5, 6, 7 dots. Okay, well, how about the fluorine ion? To remind ourselves that, we can see from the diagram that, I just want one more dot right there. That means that fluorine wants to gain an electron. And why? Because if it gains one more electron, this P sublevel would be filled, and then I would have S2 and P6, 8 valence electrons. So fluorine with 8 dots around it, but remember, that's not what it normally looks like. Normally, it only has 7. So we need to put the brackets and the charge to represent that fluorine gained 1 electron. So remember, electrons are negative, so if you get more electrons, you become more negative. So this is how we would represent, starting to show what's happening. And just kind of spoiler alert, you can maybe kind of see like, look, a positive 1 and a negative 1, maybe these two things would find each other in space, and the fluorine really gained the electron from the sodium that was giving 1 away, and then they would make a formula unit. But that's what I'm going to talk about next. So for now, pause, do a level 2 question. You could pick another atom on the periodic table and say, draw its Lewis dot diagram. That would be a perfect level 2 kind of question. Okay? All right, so pause the video, come back when you're ready. Let's finish up these notes. So you might have noticed, wait a second, this sodium had 8 dots around it. This fluorine had 8 dots around it. Why do all of the ions have 8 valence electrons? Well, remember, that's where that octet rule comes from. Every atom is considered stable if it has 8 valence electrons. Why is it 8? Because then you have a full S and P sublevel. Those are your valence electrons. Your outer electrons they're full. There's nowhere else to put things, so there's no reason to do any more bonding, so that makes the element stable. All right, so once again, what is the group on the periodic table that already has 8 valence electrons? Everybody say it. Yes, the noble gases. So if you look at a periodic table and you see this random format, some of you were trying to put that as answers the first time we learned electron configuration. So what this is saying is that this is the helium electron configuration, meaning 1s2, plus 2s2 and 2p6. So 6, 7, 8, 9, 10 is how you get neon. Argons would be the neon electron configuration, 1s2, 2s2, 2p6, plus 3s2 and 3p6 to get you to 18. So that's what that symbol means. If you see that places, it's saying it's this electron configuration plus these pieces to represent the rest of the electrons for this element. So the noble gases have 8 valence electrons. The only exception is helium because it's full when the s block is full, because there is no p block. For helium, it only has 2 electrons. All right. So the last little piece here is let's just do a quick reminder about a little bit more about ions and the chemistry of that. So remember, there's 2 versions of ions. Cation is one of them. And remember my fun little way to remember? Cats have pos. So cation is positive because it lost electrons. If you get rid of something negative, you become positive. And generally, these are the metals on the periodic table. An anion, ants are negative at your party. So an anion is a negative ion because it has gained electrons to fulfill that octet rule. And generally, these are the nonmetals. And just a reminder one more time if you need it, you've got that dividing line between kind of aluminum and silicon. So you've got that dividing line that looks like stairs. Everything on the right side of the periodic table are nonmetals. Everything on the left side of the periodic table are metals. So you'll see that there's a lot more options, but now we can kind of see why that is. Because remember, the D block and the F block, their highest occupied energy level is always going to be in the S, right? So it's always going to be easier for even the D block and the F block elements to get rid of this S block to be like the noble gases instead of trying to fill a P block, because they would have to have a lot of extra electrons to do that. But for example, then the nonmetals, they're over on this side. So they already have maybe 1, 2, 3, 4, 5, or 6, or 7 valence electrons, like a S2 and a P3, S2, P4. So it's going to be easier for them to gain electrons and fill that S and P block to fulfill the octet rule. So just again, some more connections between other things we've learned, the periodic table, why is it an octet rule, why is it positive and negative, all that stuff, trying to make all of that fit together in your brain. All right, let's do one more thing. Let's do Lewis dot diagrams with an actual compound, which is what I hinted at a little while ago. Remember that an ionic compound forms because one of the nucleus is more effective. That atom has a higher electronegativity, so the nucleus is better at attracting electrons to itself. One atom loses an electron, and then one atom gains the electron from the one that lost it. They have to go together. You can't lose randomly and you can't gain randomly. So you have to have 2 atoms next to each other in space where one nucleus is strong enough to actually pull an electron away, and you have to have one nucleus that's willing to give up one of the electrons. And then that's what forms the connection. So again, here's that visual, right? The sodium atom has a weaker nucleus than the chlorine atom. And in fact, it's so much weaker, the chlorine nucleus actually takes the electron into its electron cloud. And then look at this. So then now its outer layer of sodium is 8, and now the outer lower layer of chlorine is 8. But this had to gain an electron to do that, so it's negative. But this had to lose an electron to get this way, so it's positive. And then see how this used to have 1, 2, 3 energy levels? It only has 2 now because it got rid of that outer electron. So the next layer down was now the valence electron layer. The 2 ions, positive and negative, now connect to create sodium chloride, a bonded formula unit. And then here's just showing you in terms of electron configurations. The S1 gets transferred over here to the P5. So then now you've got a P6 for chlorine with a negative charge. The 3S goes away and you end with the 2S2, 2P6, positive charge for sodium. And then together, positive, negative. So you can see here's your Lewis dot diagram. The only thing that's missing is the brackets. And then this should have brackets around it with the positive. And you could still there's 2 ways to do it. Sometimes scientists just put the positive charge and say that, oh, it's lost its outer electrons. Or you could put the 1, 2, 3, 4, 5, 6, 7, 8 dots in the bracket around it. That's generally how we like to do it here in Roseville. All right. Okay, let's see what this looks like then. So let's do sodium and fluorine. That was actually the 2 separate ions we did earlier. So we already know that sodium has 8 dots automatically, brackets, and a +1 charge. Because the only way it gets 8 dots is if it loses an electron. Fluorine, we gave it 8 dots, and we had to put the brackets in the -1 to say that fluorine only looks like this if it gains an electron. So then now, You've got a positive one. Sodium gives this electron. Fluorine takes the electron. So now they are connected to each other from opposite charges. This is the Lewis dot diagram for sodium fluoride, the formula unit. Let's try one more, aluminum and chlorine. All right, look where aluminum is. If you look at it, count the S and the P, where it's located on the periodic table, it would have S2 and P1. That means it has 3 valence electrons. But if it stays that way, it can't bond with anything. So it wants to lose the S2 and the P1, and then it would have a +3 charge, and the next layer down it'd be 2S2 and 2P6, so it has 8 dots automatically. Chlorine right now has an S2 and a P5, 7 valence electrons. So if it gains 1, it would have S2P6. Well, where's it going to gain an electron from? Oh, from the aluminum that is giving away 3 electrons to be stable. So 8 dots around chlorine, brackets -1. So one of the electrons for chlorine came from aluminum. But aluminum still has to give away 2 more electrons to be stable. Well, chlorine can't take any more unless you have another chlorine. And I'll notice where I put it. I didn't put it next to this chlorine because this chlorine is not taking an electron from this chlorine. This chlorine is taking an electron from this aluminum that's trying to give away 3. Well, now it's given away 1, 2, so I need 1 more chlorine. Notice where I put it. If this was a 3-dimensional screen, maybe I would have put it like out in front of aluminum or back behind aluminum. But in this case, I can put it next to the aluminum here. So look at, aluminum gave away -1, -2, -3 electrons, balancing out the positive 3 electrons. This is what the formula unit for aluminum would visually look like. That is one of the new things we're adding in this unit. What do these compounds actually look like? Instead of knowing that their formula would be AlCl3, oh, there'd be 3 chlorines surrounding the aluminum. It would start to build maybe like kind of a positive negative crystal structure. Those are the other things we're going to talk about later this unit as well. But this is a Lewis dot diagram for an ionic compound instead of just an element. All right, go ahead and do a level 3 kind of question, something about predicting or imagine or defend, something like that, about any of the notes that we've taken today. And there's a lot to choose from, I know there is. And you could also do your summary, which helps you review, what did I really learn from these video notes? Pause the video. When you're ready, come on out. Come on back. All right, so that's the end of our first day of notes. I know there was lots of information, so make sure you take time to process it. Here's the things I want you to do. Finish any COSTA questions and write your summary. This is important for processing because, again, you got a lot of information in this video lecture. You got to take time to see, did it make sense? Do I understand it? What questions do I have? What questions could I ask, like quiz questions? Because those will be good review for later. If you haven't done so already, put our new unit plan into Notability so you know what are we doing each day, what are the objectives I need to know for this unit, just to kind of help yourself stay organized. You could start the Unit 9 unit practice problems. The answers are posted. You get you a chance to see what kinds of questions I might ask related to today's notes. This is another really good way to help you process it. And then that brings us to the end. Thank you so much for listening and learning more about bonding together. I will see you next time.